let's look at the concept of torque. If we had a wrench and we exerted a force at its center of mass, we would get linear motion. So the wrench would not rotate and it would just move in that linear line. However, if we were able to exert a force away from that center of mass, it would rotate about that center of mass as well as travel linear. However, now if we fix it and exert a force at a distance away from the center of mass, it will rotate around its fixed point. It's not going to just keep spinning around like that unless it's a really loose bolt, but you get the idea. So, torque is affected by a force acting at some distance away from a pivot point. Could be the center of mass, could be a fixed point. Now, this is a cross product, which the direction of R is the radial distance away from the pivot point. So in case of, if we had that bolt there, I don't know why I can't draw enough, so that's terrible. A hexagon. Okay. And the wrench was there. Got rid of my wrench. And I exerted a force at this location. The R vector will be that direction, away from that pivot point. And it is a cross product, which means that they have to be perpendicular to each other. The algebraic equation for a cross product is the two vectors, magnitudes, times the sine of, I want to say it's phi. Again, r is the distance from the point of rotation. Now, again, with these algebraic methods, it's not always the case that you have to use the sine of the angle that they give you. So you have to make sure you think through what angle they give you to figure out what function you have to use. It's more important to realize that for a cross product, what has to happen is that you either have to have a force that is perpendicular to a radial distance, or a radius perpendicular to a force. I'll try to explain the difference there. For the case of the force being perpendicular to the radial distance, if we look at this image here, the force is being directed at some angle, so that's the applied force, at some angle with respect to that radial distance. Okay, and you can see it has x and y components for it. Now, based upon that phi that's given, we can see that the perpendicular component of the force is the f sine of that angle phi. So now if we just multiply by that radial distance, we'll have the total torque acting on that object. Okay. So there's the case for the force having to be perpendicular to the radius. Now, what we can do is find the radial distance that is perpendicular to the force. All right. So in the first, when we looked for the perpendicular force, we had to use the function to figure out the perpendicular component of the force. Well, instead of using the function to figure out the perpendicular force, we're going to use the function to figure out the perpendicular distance to the original applied force. So here we're using the original distance. For the next one, we're going to use the original force. All right, so let's look at this line of action here. All right, so if we follow the force back, we can see that at some point we can make a perpendicular line to the perpendicular line to the line of action that will go through the pivot point. So this distance here makes a perpendicular angle with the line of action that is pointing in the direction of the force. So if we wanted to figure out the length here, you would have to use r times the sine of this angle phi. So if we write that out, we'll have the original applied force times r sine of phi. When our previous situation, we looked at just the perpendicular component, which was f sine of theta times the total radial distance there. So mathematically, they're identical. It's just which way do you see the problem, and sometimes the way the problem is worded or just displayed to you, it's easier to look at to solve it one way or another. So if it's not a rigid object like that, but a particle instead, let me try to get an XY axis here. And let's put a particle here. And we'll have a force being applied to that particle in that direction. All right, and this particle is going to be a certain distance away, r, from the origin. And we can know the original location of this if we just say that at that location it's at -4 position, and at this point it is at a +2 position in the x and y direction. Even though there's just this linear force and this particle will move through space and probably accelerate, there is a torque with respect to a reference point, and we're going to use the reference point of the origin. And if you can see that the radial distance as this particle moves this way, this is going to arc, and the total r distance is going to be different depending on its position. But there's actually a constant torque acting on that particle. So the way we have to look at this one is as the radial distance that is perpendicular to that applied force. So that everywhere along that linear path, that particle is always 2 meters, or whatever unit, 2 units above the x-axis, and it will always stay there. So the force is being directed to the right, the radial distance is always 2 units up. You would have to think about it in that manner in order to calculate the torque of a particle moving through space through a force. You probably will see something like that on the multiple choice.